Hello, hello. It's time to do math. Woohoo! We love some math. All right, today is day 2 of optimization. Day numero dos. Okay. I'm going to pick up with the last example that we didn't get to in our first day. This was on first day's notes. I think it's good to start here. We're just going to go with it. See how much we can get done in 30 minutes. All right, very common question. I love this question. We're bringing like coordinate planes and equations on here. It says, find the point on the line 6x plus y equals 9 that is closest to the point negative 3, 1. Closest to the point. This is optimization, so you have to ask yourself, what are we doing? We're minimizing, maximizing, what? I want to find the closest point. This is another way of saying minimizing, minimizing distance. Okay, minimizing distance. So that's going to be our Q equation. Right? It's distance. So let's draw this out real fast. So I'm looking at 6x plus y. 6x plus y equals 9. That's y equals 9 minus 6x. So we know how to graph that. Let's see what this picture looks like. Okay. Let's see, we're going up 9, so 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 1, 2, 5, 9, 10. And we're going down 6 over 1. So down 1, 2, 3, 4, 5, 6 over 1. Down 1, 2, 3, 4, 5, 6 over 1. This is what my line. All right, that's my line. So if that's my line, I'm trying to figure out what the closest I could be. So at what point on this line? So here, somewhere that is closest to the point negative 3. So negative 1, 2, 3, up 1. Okay. Now that point's not going to be all the way up here. It's not going to be all the way down here. It's going to be somewhere right here. I'm trying to minimize this distance right here. Well, how do I minimize a distance on a coordinate plane? What is a distance formula? We know what distance equals. Think back. Distance is equal to the square root of x squared, or x2 minus x1. So we'll say x2 minus x1 squared plus y2 minus y1 squared. Right, there it is. Woohoo! Okay. Now, the only thing is, okay, so remember we got our Q equation. It's got to be a couple things, right? Once we figure that equation, the next step is to make it one variable, and we need to make it that's the bell. We need to make it one variable. We need to make it simplified. So let's start with the one variable part. We got 4 different variables: x2, x1, y2, and y1. Well, notice how one of those points is consistent. This will always be the point negative 3, 1. So plug in negative 3 for one of the x's, plug in 1 for the other y. There you go, boom. So we got all but x2 and y2, so there's got to be something I can plug in for this other y equation. Well, what could y possibly equal on that other graph that we can use that we get from our condition? Oh, there it is, 9 minus 6x. So we know that y is equal to 9 minus 6x. So what this does is it makes it single variable. We got the square root of, we got x minus, or plus 3, I guess, squared, plus 9 minus 6x minus 1 squared. Yay! Okay. So we got it one variable. Check. All in terms of x. Now we got to simplify it. And I'm going to teach you a little trick with this one right here. If I take the derivative, the whole thing is a big chain. We got the square root on the outside. If I take the derivative and do chain rule, I'm going to end up having this exact same quantity raised to a negative 1/2 power if I were to do chain rule. There is a shortcut to prevent this. If I were to square both sides and say d squared equals x plus 3 squared plus 9 minus 6x minus 1. This is a trick with whenever you're doing distance formula for optimizing. If I were to take this derivative, okay, it's going to be the same maximum or the same minimum value that you would get if you did it with the square root. All the square root does is give you the same exact thing on top like we got right here, but it's also going to give you this negative quantity on the bottom, which is unnecessary for this situation. So this is a helpful trick for optimizing. You could leave the square root if you want to. Trust me, you can leave the square root if you want to. It's going to give you just extra stuff you don't need. This is a common practice for simplifying down a distance formula. So what I could really do is I could say that this is my Q equation. In fact, I can simplify this Q equation even a little bit more by simplifying this and foiling it out. And again, all it is just what the top's going to be if we left the square root, if we ended up taking that derivative. So leave the square root if you really want to. It's just going to be extra steps that aren't necessary. Okay? So what I'm going to do is I'm going to simplify this first of all to 8 minus 6x squared. I'm going to FOIL both of these. So we got x squared plus 6x plus 9 plus, and then it's going to be, if I were to do this, 64 minus, oh poop, minus 48, minus 48, so what's that, 96? Minus 96x, and then plus 36x squared. And then lastly, Q equals 37x squared. That minus 90x plus 73-ish, I believe. Now, the more I look at this, we haven't taken the derivative yet, blah, 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 blah. The more I look at this, that would be very ugly to have to factor, but thank goodness we haven't taken the derivative yet. All right, let's see. So 37 times 2 would be 74x minus 90x equals, and we're going to set that equal to 0. We end up getting, oh, that's not an x. There's no x there. I'm sorry. So 74x minus 90 equals 0. And then x equals 90 over 74, or 45 over 37. So whenever x is equal to that exact point, okay, we should have a minimum distance. So let's just test just to make sure. We'll just test just to make sure. We'll say Q prime. And we're going to test 45 over 37. And there is no closed brackets here, so we don't have to test any endpoints. And let's see, if I plug points back into the derivative, so this point right here, if I plug anything less than 45 over 37, so say like 1, it ends up being negative. Anything greater than this makes it positive. So this is indeed a relative min, because the derivative equals 0 and it goes from negative to positive. All right, and because that's the only minimum, that is my absolute minimum. Yay! Okay. So we got the x value. Now if I want the y value, let's think about the question that it's asking. We always want to answer the question. It wants to find the closest point. We got the x value. The y value will just be equal to negative 6 times 45 over 37, right, plus 9, which simplifies down to 63 over 37. You can test that math out if you want, but my closest point to the point negative 3, 1 is 45 over 37, comma, 63 over 37. So we go back up here. This point that I plotted right here seems to be pretty close to that. So we should be pretty good. It's about, that's like 1 point something, 1 point something. So that seems about right to me. Okay. Yay, we found the closest point. All right, let's go on to some more problems. The stuff from today, let's see how much we can get through. 20 minutes left. Ooh, I love this problem. Okay, farmer has 800 feet of fence and wants to enclose a rectangular area for a pen. And he's going to divide the area into 4 pens using the fencing with each side parallel to the same side of the rectangle. Find a maximum area he can enclose. Maximum area. All right, maximum area is our Q equation. That's what we're optimizing. So I'm going to go ahead and write that. We are maximizing area. Always start with writing that equation. So now, when we have the equation, go ahead and write the equation for a rectangular area. Area equals length times width. So we got our Q equation. The whole idea is, again, to get it one variable, okay, and we want to get it simplified. So we got to check those two off before we can take the derivative. So we don't have it one variable. Let's draw a picture to kind of see what's going on here, okay? We have 800 feet of fencing. That's one condition. We're enclosing a rectangular area for a pen. We're going to divide this into 4 pens. 1, 2, 3. That's very ugly drawing. 4 pens using fencing with each side parallel to the same side of the rectangle. Find the maximum area he can enclose. So I'll call this vertical distance x and this horizontal distance y. Okay? So my area is equal to x times y. But again, it's not one variable. But how can I use my conditions to get it one variable? Think of it this way. All right. We're looking for area, but the condition that we have is that the perimeter is equal to 800 feet. We are using 800 feet of fencing. That is all of these variables added together. So one condition is that the perimeter is equal to 800 feet, which is equal to all of these x's added together, there's 5 of them, and all of the y's added together, there's 2 of them. And it's this condition right here that I can use to substitute in a value over on the right. It's just a substitution property. So maybe I'll get y by itself. Okay, I'll subtract 5x and divide by 2, and if I do that, I get 400 minus 5/2 x. If I subtract 5x and divide by 2. Okay, so I'm going to take this bad boy, plug it in up here, so I get that area equals x times 400 minus 5/2 x. And boom, right there, we can check off the one variable. Now the idea is to simplify. Okay, so area equals, and I think the best way to simplify this would be to just distribute the x, and we get just a nice little quadratic. Okay, so we got one variable, check. We got simplified, check. And now the rest of it is just identifying the max, a relative and absolute max, using our calculus properties, right? So, let's see what we got. I'll make this my Q equation. So Q prime is equal to 400 minus 5x. Setting that equal to 0, we get 5x equals 400, or x equals 80. So if I make those x values equal to 80, then hopefully that would end up being a minimum. Let's test that point real quick. Let's test x equals 80. Okay, we're going to test it in our little Q prime. We're going to test it doing our derivative over here. If I plug in, let's say 70 or anything less than 80, I end up having a positive number. Anything greater than 80 is going to be a negative number. So because the derivative is equal to 0 and we go from positive to negative, we are going to have a relative maximum. And since this is the only time that it changes, this is going to be an absolute maximum. There is no other points to check. We don't have endpoints because it's 0 unincluded. You can't have a length of 0. And it's up to 400. as the maximum that the x could be, but again, that's not going to be possible because it would take away the two-dimensional shape. So we can't check any endpoints. There are no endpoints to check. So it's asking for the maximum area. So we got that x is equal to 80, so that's good. We need to figure out what y equals. And remember that y is just equal to 400 minus 5/2 x, so 5/2 80. So y equals, in this case, what would that be? 40 times 5, y equal 200. So the maximum area, given those conditions, is just equal to 80 times 200, which is equal to 16,000. I think the units were feet in this case, so feet squared. Given that I use all of those fencing requirements, the max area I can have is 1,600 feet squared. Okay? We figured out that each of these are 80, and this length is 200, and we got the max area given our conditions. Very nice. Very nice, very nice. Let's keep going. Optimization. Okay, so this is starting off with some more types of problems. Ooh, I love this problem too, and y'all should as well. This is just a little description of a relationship between two numbers. Let's see what we got. Find a positive number. Okay, so that's 0 to infinity. Find a positive number, and we don't include the endpoints there, so we don't have to check the endpoints, such that the sum of the number and twice its reciprocal is as small as possible. So we're trying to take the sum and make it as small as possible. So we are minimizing our sum. That's going to be our Q equation. So it's going to be the sum of two numbers. All right, the sum of two numbers. So how am I going to write that? Sum equals the sum of two numbers. Now, one of the numbers, so the sum of the number, we'll call that x, and twice its reciprocal. Okay, what does that mean? Twice its reciprocal. So that's going to be double its reciprocal. Now, its reciprocal is just 1 over x. So I'm trying to minimize this sum, the sum of a number and twice its reciprocal. So once we get that equation, we have to make it one variable and simplify it. And if you notice in this case, all the variable is x, so it's already one variable. Let's just simplify it a little bit. How about 2 times x to the negative first power? Wouldn't that make it a little bit easier to take the derivative of? So in this case, q prime equals 1. If I do the derivative here, that's going to be minus 2x to the negative second. And I'm going to set this equal to 0 and hopefully solve for a minimum value. We're trying to minimize the sum. Okay. So I think that's not too terrible. We could say 1 minus 2 over x squared equals 0. 1 equals 2 over x squared. Maybe multiply both sides by x squared and take the square root. And if I take the square root, I get x is equal to plus or minus the square root of 2. But remember that we only are looking for positive numbers, so we're going to reject negative square root of 2 because it's not in our domain. Okay? Always reject a solution that is not in your domain. Okay. So we're going to test that point. We're going to test x equals the square root of 2. And verify that that is indeed a minimum value. So we got q prime, I got the positive square root of 2, and I'm going to test this point in my derivative function. And pick the derivative function that's easiest to plug it in. Like, I know this is my derivative, but it's easier to plug it into the one with x squared on the bottom. So if I plug a 1 into that, something less than the square root of 2, it's going to end up giving me a negative number. If I plug anything greater than the square root of 2, like 4, 5, 6, or 7, that's 1 minus a small fraction, which is a positive number. So what we have here is a negative to positive. This is where f prime equals 0 and where it goes from negative to positive. So we have just checked and verified that this is indeed an absolute minimum. There is no other point where we change from negative to positive, and there's no endpoints to check. So it's an absolute minimum. So we verified that. What is the question asking us to find? It says find a positive number. Well, we don't have to do anything else. We figured out what that positive number is. It's just the square root of 2. Okay. If I add those two together, if I add the square root of 2 and its reciprocal together, doubling it, it will be the smallest sum possible. Okay. Nice. And let's see, we're at minute 20. We can probably get at least, well, maybe one more. That'll leave. We'll probably do this one and then leave the last problem for class. The last problem for class is a good one. So let's see. It says find the maximum area. Boom, bingo, bongo. Find the max area. Bam, right there. Max area is my Q. All right. Of a rectangle inscribed between the x-axis and negative x to the fourth plus 3. Don't let that confuse you. Let's go ahead and consider what an area equation is and how we can get it one variable. Area for a rectangle is length times width. Start there. Now, the conditions are what's going to help us get the length and width in terms of the same variable. Since we're talking about an x and y coordinate plane of function here, it looks like that variable is going to be x. So let's figure this out. If you were to graph negative x to the fourth plus 3, it's just a parabola that's been flipped and up 3. So if you graph this, you're going to notice that the function looks pretty similar to just a quadratic. It's going to look something like this. Okay? Now, I'm trying to figure out how I can use or how I can inscribe a rectangle in there and between the x-axis. Inscribed means that the corners are touching the x-axis and the function. Okay, so it looks something like this. It's going to go down, touch the x-axis, and because this function is reflective across the y-axis, it's going to go straight across, down, looks something like this. Now that's just one rectangle. I mean, I could have the rectangle look like this or like this. I mean, there's an infinite amount of rectangles that I could potentially draw. But my goal is to find the rectangle that's inscribed with the largest area. So the picture I draw, I'll assume looks like this. Now, I got this rectangle drawn. I need to figure out its dimensions, its length and width in terms of x and y. Well, think about this point right here, maybe. It's going over a distance of x and going up a distance of y. Okay? So that distance of y right there is actually my height, or my width, if you want to think of it that way, which is nothing more than negative x to the fourth plus 3. So my width is just going to be this y value right here, which again is negative x to the fourth plus 3. That's one dimension. And my length is just the value of x. We're going over x up y. If I go over x, that's half of my length. The other half would be this negative x value. The full length would be 2 x's. So my length is 2 x's, and my width, or my height here, I guess, is just this y value, which another way of saying that is negative x to the fourth plus 3. So that was the tricky part, is having to know how to graph it and draw the picture, understanding an inscribed rectangle, and then understanding how to figure out these dimensions in terms of x and y. The length is just 2 x's, and the width, or the height, is just the function negative x to the fourth plus 3, because it's a length of y. Okay? So we got it in terms of one variable, check. Now, to get it simplified, I'm just going to distribute. That's it. So it's going to be negative 2x to the fifth plus 6x. And now it's simplified. I can call it my Q equation. So now that we have the conditions all drawn out, we have the Q equation, all we have to do is just do the same old math as we're used to doing. Q prime equals negative 10x to the fourth plus 6 and set it equal to 0. Okay. I'm going to subtract 6 and divide by 10, so I get x to the fourth equals negative 6 divided by negative 10, or which reduces down to 3/5. And I'm going to take the fourth root. So the fourth root of 3 over 5 is going to be that, that x value, all right, that I have to travel to have that inscribed rectangle with the maximum area. Let's test that and make sure that is indeed the maximum. So we're going to test Q prime. And we're going to test the point, the fourth root of 3/5, which I would assume is a really small number. I think if I end up plugging in like 0.1 or 0.01 to test to the left, right, I end up getting a negative small number plus 6. I believe it's going to be positive. And you can test any point you want in this derivative, but again, I believe it's going to be positive. If I plug in a super duper big number, it's going to be a big number times negative 10 plus a small positive. That's going to end up being negative right here. So because we only have one change from positive to negative, and this makes the derivative 0, this critical point is an absolute max. So it's at this x value that we maximize that inscribed area. Okay? But what is it asking for? It's saying find the maximum area inscribed between. Okay, well we got part of the length. Remember, it's length times width. My length, there we go. My length is equal to twice whatever that x value was. So it's equal to twice the fourth root of 3/5. And my width is just equal to the same as my y value at that point, which we said was negative fourth root of 3/5 to the fourth power plus 3. Okay. So so we got our dimensions. So if I multiply these two together, just to give like a little decimal approximation here, we end up getting our area that's maximum to be approximately 4.225, and I guess it's just units squared. So test that out. This is my length, this is my width. You can test those out by multiplying them and see what you get, but I believe I got 4.225 units squared. Okay, so we maximized the area. That's awesome. Tomorrow we'll finish up with this problem, and then we will be done. All right, so only one problem in class together, and then you have a worksheet that you can do, and I would do these 5 problems on the worksheet. Okay, that's what hopefully most of the class will be. All right, good job, guys. I hope y'all have the best day ever. I'll see y'all later.